All right, this is the part 2 of the Intro to Probability, and we're still working with cards. This gets a little bit more challenging though, and hopefully this will convince you that choose notation, if you can go there, much easier, better way to do these problems. Okay, so this time you're dealt a 5-card hand. So what is the probability of getting a full house, which means 3 of a kind and 2 of a kind, or 3 of the same rank and then 2 of the same rank? Okay, so we need 3 of one rank and 2 of another. So let's first do the denominator. There's 5 cards, so how many 5-card hands are possible? That's 52, choose 5. Okay, so let's choose the rank for the 3 of a kind. And I'm going to choose that separately than choosing the 2 of a kind, because the 2 of a kind is different. So if I were choosing 2 of a kinds, then I'd do 13 choose 2. Because they're 2 of the same thing, 2 pairs, so I'd have to account for order there, but because I'm doing one that's 3 and then one that's 2, I don't have to account for order, so I'm going to choose them separately. So I'm choosing from the 13 ranks, I'll choose 1 to be my 3 of a kind, and from that rank there are 4 cards, and I want 3 of them. I want to choose 3 of them because I need a 3 of a kind. Okay, so now let's choose our pair. There are 12 ranks left. I'm going to choose 1 of them. And then there are 4 cards in that rank, and I want to choose 2 of them for my pair. Okay, well, let's try to see what this would be if we talk about independent events. So here's where it's going to get tricky. So first card, again, doesn't matter. And then let's talk about, okay, let's do our 3 of a kind here. So I've got a first card. There's 3 left in that rank, and there's 51 cards left. Then there are 50 cards left, and there's 2 in that rank. So now I've got here's my 3 of a kind. We'll just say A. Okay, so now there's 49 cards left. I'm not choosing from, I don't want 4 of a kind. So I need a totally new rank. So there's just 48 cards I can choose from. And then once I have that new rank, there are 3 cards from that rank left, and there's 48 cards left. So let's just say this is my BB. Well, the reason that is just that right there is not the total probability is I assumed an order there. I assumed that I was getting first my 3 of a kind and then my pair. But couldn't I also get, for example, you could get your pair first, then 3 of a kind. Or I could get 1 from the 3 of a kind, then 1 from the pair, 1 from the 3 of a kind, 1 from the pair, 1 from the 3 of a kind. So there's all different orderings here. So right now, by just doing this order, I'm understating, I'm undercounting, or the probability is smaller than it should be. So I've got to multiply that probability by the number of ways I could get my 3 of a kind and my pair. So I would multiply these independent events by 5 factorial, the number of ways of ordering, if we look at those 5 letters, 3 A's and 2 B's, but I've got to divide out the repeats, 3 factorial, 2 factorial. So again, more complicated when you do independent events. All right, let's do something different. Another one of these cards problems. Let's block this off here. Okay. Now we want the probability of 3 of a kind and 2 unmatched cards. Okay, so let's do the denominators the same. How many 5-card hands could I get? And okay, so a 3 of a kind, I need to choose my rank for the 3 of a kind, and within those 4 cards, I need to choose 3 of them. Now 2 unmatched cards. So Their order doesn't matter of these match cards, so I need to account for that. So let's account for that by, and I need 2 different ranks. So from the 12 remaining ranks, I need to choose 2 of them. And I need to take 1 from each. Okay, so, and so that's the choose notation. Now let's think about what we would do for independent events, and this is still getting tricky. So we would still do 52 over 52 times 3 over 51. This we're doing our 3 of a kind. 2 over 50. So that's my A. But then I've got 48, just like before. 48, because I don't want the same of the 3 of a kind, over 49 times, but then I need a totally different one. So 44 over 48. So what do I have here? Well, I have 3 of the same kind, and then I have unmatched. All right, so again, I'm undercounting because I'm assuming an order. So I need to, even though the unmatched are not the same, not like the pair, they're still 2 unmatched. So it's kind of like getting repeat letters. So you've got to multiply this by, just like before. This 2 would be multiplied by 5 factorial, 3 factorial, 2 factorial. Okay, so, which is confusing because the unmatched, they aren't matching like a pair, but they're both unmatched, so they are the same thing in that sense. Again, doing independent events gets very confusing. All right, so let's do part C. Part C here is I want 2 distinct pairs and 1 unmatched card. Okay, 52, choose 5. That's the number of ways I can get a 5-card hand. And 2 distinct pairs. All right, so I want to choose from the 13 ranks 2 that are going to be 2 ranks for my pairs. And so from the first rank, there are 4 cards, and I want 2. And same from the second of those ranks. Okay, so now I have 11 ranks left, and I just want 1 of them for my unmatched card. And there are the 4 cards in there, and I want 1 of them. Okay, now, this is the last one. I'm sorry I'm laughing, but this is where things just get so tricky when we talk about independent events. Okay. So here we have, so as always here, the first card can be anything in these cases. And if we're talking about pairs or not a specific type of card that you need first. So first card can be anything, but once I've gotten that first card, if I want a pair, I have 3. The probability of the next one matching is 3 of 51. And okay, so we'll say that's pair 1. And then let's, now I have 50 cards left, and the probability, I can choose any card that's not matching to the first 2, so that means there's 48 cards left that I can choose from. But once I've got, here's my pair 2, once I've got that, I need to make sure that I get a matching here, so 3 out of 49 is the probability there, and then I want a 3rd unmatched card, so that means 44 cards left to choose from that don't match the first 2. This is my pair 2. And that was out of 48 total cards. Okay, so we're going to call this unmatched. Now, so and you could think of this as A, B, B, and then I'll just say U for unmatched. So you would think, okay, this is, I'm going to multiply this by, it's kind of the same as the lettering before, because right now I'm assuming an order. So let's multiply this by 5 factorial, and then dividing out the repeats, 2 factorial, 2 factorial. The problem is this is overcounting, because the order of the pairs does not matter, right? So in other words, AABB is really no different than BBAA. Because what you're just saying with this probability, the one we found specifically was probability 1 pair. This was the order we were assuming. 1 pair, the second of that pair, and then another pair, and the second of that other pair, and unmatched. Well, that's no different than probability of putting the B's first, right? It's still getting one of the pairs and another. So I have to divide that in half. So this is why it gets so tricky thinking about this in terms of independent events at times. All right, last problem here is the flipping a coin. So I've got 7 coins. So what is the probability that you get exactly 3 heads? So say tails, 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 tails. I've got, 3 heads. That's the probability of getting the 3 heads. And then the 4 tails, well, half, a half, a half, a half. Well, so it isn't though just 1/2 to the 7th. I have to, because that's again assuming an order, I have to multiply that by the number of ways from my 7 coins I can choose 3 of them to be heads. Or in other words, this is saying 1/2 to the 7th times 7 choose 3 just means 7 factorial over 3 factorial, 4 factorial.